This special seminar in honor of Dr. Dick Kronmal retirement. So I'm A.R.D. Lila, an assistant professor in the Department of Biostatistics. I will do a brief introduction, which will be followed by some remarks from Dr. Fleming. So Dr. Richard Kronmal got his PhD in biostatistics from UCLA in 1964. He joined the University of Washington right after, first as an instructor and then as an assistant professor in the Department of Preventive Medicine. He joined the Department of Biostatistics as an associate professor in 1970, which is the year when the Department of Biostatistics was funded. He became full professor in 1975 and got a joint appointment in the Department of Statistics in 1987. Literally too many achievements to be listed here, but I will mention that he was elected fellow of the American Statistical Association in 1981 and has published more than 400 journal articles, both on statistical methodology and applications. In the last 20 years, he's been instrumental in running the MESA study and has been the PI of the coordinating center for many of those years. So at this point, I'd like to invite former chair, Dr. Fleming, to say a few words and maybe provide some historical background.
Yeah, great, thank you. So Dick, can I have 30 minutes? You can have the whole hour. Well, it is a privilege to see all of you here today and to see Dick here today. Just to share a few thoughts up front. I first came here in 1984. And when I arrived, it was already incredibly clear that this was a remarkable place, that UW was clearly a premier biostat program in the world. I knew that before I came. But when I came to visit, what struck me as amazing was how remarkably collegial an environment it is here. And those kinds of things, remarkable quality and collegial environment, those things don't happen passively, they happen actively. They happen with remarkable people's commitment. And we have many. I mean, we have, at that time when I came, we had Pat Wall and we had Paula Deer and Al Hallstrom and many others, and we had Dick Kronmal. And it was very clear to me as I had a chance then to be here and be experienced in this setting, how influential Dick was to that, to his commitment for excellence and his caring for other people. And that was very, very apparent in the program. And as I then got involved in teaching students, I felt like it's great to be a biostatistician, to be able to make a difference. And among the things that I think of that help you make a difference is I call it the science, the art, and the communication. Yeah, it's important to understand the science, the theory, but it's also important to be able to understand how to effectively apply that science and real world problems to make a difference. And then because we're interdisciplinary, to communicate effectively, orally and written. And Dick's been one of my role models for 40 years in those qualities. When I try to teach students, there you go. I mean, in terms of the science, the art, and the communication. In science and in art, I felt very strongly in our program how important it was that we had rigor, that we had the 570s and we had the 580s, and Dick was always a strong advocate of that. And as part of that, he was a co-professor with an appointment in the Department of Statistics and Biostatistics, because part of what made us great was the strong linkage that we had between the two in stat and in biostat, and Dick was a key part of that. And in the arts, Dick, there can't be many people in the world that have been as successful as Dick has been in getting NIH grant funding, in running and working with collaborators in the CHS and MESA programs. And that has been so critical, not just for what Dick does in making a difference in the art, but in exposing so many of us as colleagues who are students, fellow students and faculty members of being involved, providing us the opportunity to do so, providing the research funding. And when I was department chair and had an incredible great fortune of doing so under Pat Wall as my dean and Gil Oman as my dean, it was a blessing to me to have the research funding that we had created by the indirects that Dick created by his research. That empowered us to be able to pay for extra staff. We didn't have that funding from the state. That's how we funded our staff. That's how we funded the non-tenured faculty to be involved in teaching and student funding. And we created a career development pathway. Dick was integral to creating all of those. And one last thought, you know, you have a remarkable leader when they set up a pathway for those of us to follow them. And so as an example of that, this is my favorite week of the year. It's exam week, spring quarter. Why would that be my favorite week? Because this is when we do the site visits for our Biostat 24 clinical trials class. So when we start the quarter, I tell the students, I hope you like the lectures, but students repeatedly say their favorite part of the class is the group project. And so what we do in that class is we begin the quarter and we take the students, we have 40 students, we form them into 10 groups of 4 students. And each of the groups is homogeneous in that I want to do cardiology, I want to do oncology, I want to do COVID, but they're heterogeneous by discipline because quality research doesn't happen by a single person. It happens with the synergy of putting together people that are very good at the clinical side. So we have a couple clinicians in that group of 4, and we'll have a couple of quantitative people, a couple statisticians. And then during the quarter, they develop a research protocol for a randomized trial with the Fields function survives endpoint written as a grant proposal. And then at the end of the quarter, they defend their research to their peers. And so we have 2-hour site visits. And so if we have 40 students, that means we have 20 hours of these 2-hour site visits. So if you're group 3, then you spend that 2 hours critiquing a separate group 2. And then in a separate 2-hour period, a group 6, then you are critiquing them. And it's the most amazing experience to see these graduate students taking the learnings that they had during the quarter, integrating with each other. And I'm thinking so often at the end of we just did this 20 hours on Monday, Tuesday, Wednesday. I'm thinking if medical research would be done at this quality overall, what an incredible difference it would make for the world to have this experience. So why am I telling you that today with Dick here? Because this idea didn't come from me. This idea came from Dick, it came from Pat, it came from my predecessors, people going before us. Dick taught me this concept that the best way to really teach your students is to have them involved in the real experience. And he set up that process. And so following his pathway for the last 30 years, we've been doing this same thing. We've now taught 1,000 students in this process, and many of them have gone on to make significant contributions in clinical research. And this has followed the pathway of what Dick taught us about how best to teach students. So it's remarkable. Many of you might know Dick well, and yet not realize the depth of what he's done, because he's very humble. Dick doesn't do what he does for Dick's benefit. Dick does what he does because he cares about what's right, and he cares about influencing others to do what's right and to do what's right for other people. And in fact, that has allowed us, following him, to make a meaningful difference. So what I'd like to have all of you do is welcome Dick for his presentation and join me in thanking him for what he's done for all of us.
Well, that's really hard to follow. Yeah, I'd like to sort of say that without Tom and Pat Wall and the other wonderful chairmen we've had all over these years, none of that would have been possible. And if time permits, I will actually spend some time on what I would call the prehistory of biostatistics at the University of Washington. That is the part of the department, before we had a department, what led us to where we are today, really, basically, foundations. But before that, I had to give a seminar. So I've been working off and on for a couple of years now, ever since the pandemic started, actually, on a topic that's interested me for a long time. And that topic really has to do with the choice of link. What do I mean by that? Well, the choice of the model you use to estimate various parameters. And as you'll see, when we go on, how do I do this? How do I go on to the next slide? This. Oops, I went too far. That's a whole talk there, guys.
Yeah, you can see it here, sir.
Okay. One of the main principles that I want to talk about today is sort of what's involved with being a scientist and doing data analysis and actually analyzing data. And the first principle that I think is the most important is that when you're doing analysis, you want to estimate what is important scientifically or medically. And that, as you'll see, is not what is often done, maybe not what is usually done. So that is the overwhelming thing. And in giving this talk, I had a real hard time deciding what my audience was and how much my audience knew. And so I may be talking about some things that are obvious to all of you. Others will not be, particularly when I get to the Lee-Duan theorem. Starting from that is, next slide here. First, I'm going to talk a little bit, very briefly in the beginning and a lot more later, about the generalized linear model in medical research. And for binary outcomes, the question is, what parameters do we want to estimate? What are the important scientific questions we want to ask, and what will measure those? So oftentimes, for statisticians, they focus on the link in the generally, that is what the model is, and what the error distribution of the model is, and less focuses on what you're actually estimating. And that's, in my view, is a mistake, and a big one. So I'm going to talk about that topic, the insights and implications of the Lee-Duan theorem. Okay, this again, I won't spend much time on that because all of you know what the linear model is, a generalized linear model. But for binary variables, we're trying to estimate the betas, that is the coefficients that are involved in the prediction of y. Y is a very general function, that is the link is g. And I'll talk a lot about that. I'll talk almost nothing about the error term because I don't think it matters a whole lot in most instances. Okay, well, let's see, what do we want to measure when we have binary outcomes? Well, there are three kinds of measures that are typically in use. The risk difference, which is the difference in the probability. I'm only talking about this now for a binary outcome, but everything I say extends to continuous variables as well, and more than one variable. But the risk difference is the probability of y is 1, namely that the outcome occurred given that the risk factor is present. And then the risk difference is just the difference between that probability and the probability that you get if the event did not occur. I mean, the risk factor did not occur. And then people use the relative risk, which is just the ratios of those two quantities. And then people use the odds ratio, which I had trouble putting it on the screen at one time. Basically, it's the ratio of the odds of having a 1, that is for x equal 1 and for y equal 1, versus the probability of having a 0. And divided by, obviously, the odds of having a 0. And in my experience, when I was young, my father used to bet on the horse races. And he was a much bigger expert at the odds than I ever have been. And he didn't use the odds ratio, but he did use very sophisticated decision-making process of figuring out the odds versus the return on investment, essentially. Anyway, there are many methodologic and philosophical papers that the odds is the odds man out when it comes to be a measure of medical interest. And I think it is, in my view, very rarely that it really is what we want to estimate. Okay, there's a lot on the screen. I tend to be too verbal here, too verbose maybe. There's a paper in a journal called The Evidence-Based Medicine from 1986. And its title was Down with the Odds Ratio. And this was written by, at the time, very famous statisticians who were at Cambridge and at Oxford. And their point was essentially that the odds ratio essentially overinterpreted, didn't measure what we wanted to measure, and therefore shouldn't be used. And they're probably primarily talking about, in fact, clinical trials and observational studies when you only were interested in a single risk factor. And then 1 year later, a well-known epidemiologist, really one of the most methodologically oriented epidemiologists of his time, Sandra Greenland, said basically that if you want to summarize exposure impact on risk, and then you should either measure the risk difference or the risk ratio, namely the relative risk. And that he was really speaking about why you don't want to use the odds ratio. And finally, in JAMA, rarely recently, there was in their what they call the guides to statistics, they talked about the odds ratio and what they thought were the current best practice in use. And they pointed out the limitations of the odds ratio. And first was the fact that the odds ratios are often interpreted as probabilities, a ratio of probabilities, and they are not that. And also another quality of the lack of quality of the odds ratio is less well known at all, is that the odds ratio will change as you add variables to the model, even if the variables you're adding are totally independent of the variable, the risk factor of interest. And that comes, by the way, even if you add variables that are associated with the outcome and the variable of interest, the risk factor of interest, still the effect of it makes it sort of hard to determine what is confounding and what in fact is a true measure of the risk. And the odds ratio is not a good way of doing that, determining that. So in the medical literature, by far the most common statistic you see is the odds ratio when you're, again, in the context of prediction of a risk or finding a risk factor that's associated with some outcome. And again, as I mentioned, it is not based on the fact that they really want to estimate the odds ratio. I think in most cases, the physicians who are writing these papers have no idea what the odds ratio is. And they often, and not always, interpret it incorrectly. Well, I don't want to spend too much time on this, but there are numerous, I could have found 100 examples of the misuse of the odds ratio. And here are 3 of them. I just went basically to the latest issue of, I get JAMA's various journals on the internet coming to me every week on my email. So I just picked one of the journal, and the one I picked happened to be JAMA Network and then COVID-19 updates. And what you can see is that in these 2 examples, by the way, there are only 7 papers in that issue. And 2 of them had the odds ratios misinterpreted. One had the relative risk misinterpreted, which I'll get to in a minute. And the others, 2 of them had Cox model results and the other was just descriptive. So essentially almost all of the inferential epidemiology was presented were basically overinterpreted results using odds ratios. And in fact, if you read these, you can sort of see that they didn't understand what the odds ratio was. Otherwise, they wouldn't have written what they wrote. And likewise, as I say, there was one other article in that issue where the relative risk was presented. And again, what they said was there was a 30% lower risk of developing, in this case, PCC, whatever that is. And in fact, that's not the risk difference. And it's not even clear what they mean by 30% lower. And so, and again, this is the common misinterpretation that's made. And then I want to talk a bit about why you don't want to use it. By the way, these are all preambles to the content of this, but unless you understand why I'm doing the paper, the talk I'm doing, you need to understand these preambles. And the next step in my evolution, basically, and in the evolution of this talk, was the notion that instead of relative measures of effect, what you really want is absolute measures of effect. And therefore, even though 6 years ago I was talking about the relative risk, my last seminar I gave was why the relative risk was a good thing to do, and you should replace using the odds ratio with the relative risk. In that time, my thinking has evolved to the point that I don't think you should use relative risk very often either, that instead you should use the risk difference. Okay. And there's a very interesting paper that I came across, not because I was searching for it, it happened to end up in my email. And there was just the list of all the papers that were in that issue of the Journal of Philosophy of Science. Now, I have to say, I don't read journals of philosophy of science very often. In fact, it's never. But I happen to have this one, and I looked at the list of papers, and I saw this one, 3 arguments for absolute outcome measures. And when reading it, it struck me that this actually described why I thought that absolute measures were the appropriate thing to do and not relative ones. And I won't go over these other than to say that the biggest one is this cognitive bias, in that if you're going to misinterpret what the meaning of the odds ratio is or the relative risk, then it doesn't matter essentially, because you're going to overestimate what the efficacy of treatments are. And that's done a lot. And then you had a decision theoretic that absolute measures are better than relative for making a decision. And that makes a lot of sense too. If you were a patient and I tell you that the relative risk of you having some outcome is 10 times bigger if you have this treatment than if you have this other one, you say, well, 10 times as much, that's really a lot. I want the other treatment, the treatment that gives me a benefit, the one that has 1/10 the risk. But in point of fact, that doesn't help you if you don't know what the actual probabilities are. So if the probability was 1 in a million of you having the event and taking this very toxic treatment, I'm sorry, it's 10 in a million, and taking this very toxic treatment, cut it to 1 in a million, 10-fold relative risk, you still might not want to take that medication. And again, you see that all the time. And one thing I think my great friend and colleague Tom Fleming will appreciate is that in cancer research, they also use relative measures most often. They use Cox model, hazard ratios. But they do one thing that I think is really interesting and is a good lesson, is they also use the difference in median survival. Okay. So if you will live 3 months longer on this treatment than this other one, that's fine. But what if the hazard ratio is 1.5? And all you're going to gain from being on this treatment is 3 months in terms of, say, your survival or your time to remission. But at least they give that information. They give the absolute difference of the medians of survival time. The only problem with that is that sometimes the medians haven't occurred yet. So you really, in that case, they will say not reached. So it doesn't help you then. But the point I'm trying to make is, though, in every one of the papers I read nowadays on the results of clinical trials and cancer research, the quantity that is emphasized is the hazard ratio. And actually, I think that's wrong to do, because that is not what the right measure of benefit is. Anyway, going on, and then there's a causal argument. And again, it's the same sort of thing, is that if you want to interpret the results of clinical trials, or where you seemingly can, or epidemiologic studies where you really shouldn't, you're interested in causality in the end. And relative measures are not very good at capturing what you want to know when you're interested in causal outcomes. Well, I think the risk difference is the quantity of interest in most medical research. Now, in clinical trials with binary outcomes and two treatments, always the risk difference is calculated or is at least referenced in the sense that the probability of getting cured if you're on one treatment versus the probability of getting cured if you're on another are both presented. So you can calculate the difference between the two, and that's in a sense the benefit of the treatment. As I said, the problem in clinical trials nowadays, at least in some fields, is that the relative risk is often used as the measure that is emphasized in the paper rather than that difference. But at least you have the difference there. And then usually when you test the difference in the response, the probability of getting a positive response versus not. In epidemiologic studies where the binary risk factor, the individual risks are often displayed but rarely emphasized. So, and in some cases, you can't even find in the paper the actual risks, the probabilities. You only are shown the odds ratio or the relative risk. And again, that's one of the big problems we face. Okay, well, how do you estimate the risk difference? And now it's obvious how you estimate it if you only have one outcome and one binary predictor. You know, it's just the difference in the probabilities. However, if you want to estimate the effect of some continuous variables and other binary variables in a single model, like you do in epidemiology typically, you have to be able to estimate the risk differences. And that estimate, those estimates are obtained by simple linear regression. And when I say that, oftentimes my statistical friends say that can't be right, because how can you try to predict a binary variable? In other words, do a linear regression when the outcome is 1, 0. And the answer I will give, and I'll show you this later, is that yes, you can do that. And the risk difference, because it's the quantity of interest, is what you actually should be estimating. Well, obviously, we all know how to do linear regression. It's simple. So why isn't it done very often? Well, there are several reasons. I've had comments made when I've put the risk difference models, the linear regression, in journal articles that I've written, that I've been a co-author of. One time, the reviewer came back and said, the model is incorrect. Now that's kind of hard to answer to someone who says that, because you don't know why they thought it was incorrect. But nonetheless, I had to answer it because otherwise they wouldn't accept the paper. So I argued it was the quantity of interest and there was nothing incorrect about it. It was no more or less correct than using other models for binary variables, logistic regression, for example. And the reviewer accepted it. I don't think the reviewer was a statistician. What the reviewer did and what the journal did might have been two different things. That is, they might have liked the paper and didn't care what the statistical reviewer said, which is often the case. Or he or she was satisfied. The other one I got all the time, and from again in different papers, is that when you estimate the linear regression of y equal 1 or 0, you're estimating the probability that y is equal to 1 or 0. Okay, that's what the model is estimating. And that's not particularly good in the sense that the estimated probability can be greater than 1 or less than 0. Obviously, you don't want to estimate probabilities that are outside the range of what probabilities can be. Well, that is a problem. And I'll get back to, in a minute, I'll tell you why I think it's not so crucial as it's made out to be. And then I won't go into much about homoscedasticity, in that it's just that the variance of the probabilities of the coefficients rather, are a function of the mean. which is not a good thing to have happen. Well, there's a nice, wonderful paper actually, and I don't know if any of the authors of that paper are here. One of them can't be, he's in New Zealand. Of three members or former members of our department, Thomas Lumley, Paula Deere, and Scott Emerson. Two of them are retired, and as I say, Thomas Lumley is in New Zealand. And it's really a wonderful paper, and it's one I think is the one I send people to whenever, particularly physicians, whenever I want them to understand that normality isn't important, which they always think it's very important. But it's this paper is much more than that. It's about what you should do in terms of choosing what you estimate. And the normality comes in because sometimes reviewers or the people writing the papers will say, you can't do this because the outcome isn't normally distributed. But the paper is about much more than that. It's also about choice of models, choice of link. And in this paper, they really answer those three questions that I put up before, the criticisms of using the risk difference. And I'm paraphrasing some of the things they said, but there's a famous statistician whose name I've forgotten that once said, most models are wrong, but some models are useful. George Box. That's what I thought it was, but I didn't want to say so because I didn't know. I didn't remember for sure. Anyway, it is the point there is that you want to choose the model that gives you estimates of things you want to know. And so that argument I've used, as I say, when papers I've written that use the risk difference are criticized. Well, the other one that P, the probability can be less than 0 or greater than 1. My answer is I don't care because I'm not using it to estimate the probabilities. Clearly, I don't want to use that to estimate the probabilities for that very reason. What I want to do is estimate the risk difference. And it gives, least squares estimation, which is what I use to estimate those coefficients, is correct. The coefficients are asymptotically unbiased, consistent, and there are other nice properties. So it's the estimate of those risk differences I'm interested in, and whether or not the probabilities are estimated accurately or not is not the point of why I'm using it. And then Thomas Lumley, I'm sure, in that paper says that the homoscedasticity is not a big issue because as long as the proportions, the probabilities are between 0.2 and 0.8, the variance is approximately constant, and therefore it's not really a problem. Now, I'm now beginning to get to, I want to go fast because one thing I'm trying to go fast on is I do want to talk, if people are interested in, the prehistory of biostatistics at the University of Washington. That is the history before we became a department. And I don't think anybody here probably knows anything about that actually, except me, because I've lived a long time. And what I've written here is maybe a little dense. Oh, I'm sorry, I gotta go back. How do I go back here? What? Oh, back arrow, that figures. Perfect, thank you. Yeah. I don't want to take too much time on this, especially in this kind of a talk. But what this paper was trying to show, basically, is that if you use if you estimate parameters from the generalized linear model, and you have totally the wrong link, the data wasn't generated by that linear model, that link. And it doesn't, and even if the error term is completely wrong, distribution of the error term is completely wrong, that if some of these conditions that are now shown below are true, then the beta that you estimate is proportionate to the true beta of the true model. Okay. So in other words, even if you totally have done the totally wrong thing. You've used the wrong link. You've used the wrong error distribution. You've estimated the coefficients. They're still informative because you can take a constant unknown to you, multiply it by those coefficients, and you will get the coefficients of the true model. That's an extraordinary and surprising thing to be true. The problem is, as you'll see, in this paper in 1989, by the way, it's in the Annals of Statistics, the most theoretical of all statistical journals. One, I used to subscribe to it, and I would try to read some of the papers, usually without much success. And in this particular paper, the theory is really hard. And I didn't understand it then. I surely don't understand it now. But the general gist of it, I did get. And the gist of it is just what I've said. And the conditions that have to be met seem to be reasonable, at least conditions 1 and 2 that are shown there. Condition 3, however, is completely unintelligible to me. I have no idea what it means. So I don't have any idea if it ever is true or not. And when I was reading the paper, when the authors discussed what these conditions meant, he makes the point that condition 1 is satisfied for many important estimation procedures and includes least squares, generalized linear model, influence functions, maximum likelihood, anything you really want to do that we do routinely, it works for that first condition. In fact, he shows it's actually true for Cox model, which doesn't fall into that class. Condition 2 was usually satisfied. It just means that you need to be able to get an estimate of the parameters. The third one, he says, looks rather restrictive. Okay, well, that's an understatement because he says it's satisfied when the regressor variables, it says variable all the way through, but he means variables, is normally distributed or is elliptically symmetric. Well, at least in multivariable analyses, I've never seen data that could possibly be elliptically symmetric. Usually we have binary variables. Okay, the continuous ones we have are clearly mostly not even normal. So multivariately, they're not going to be multivariately normal. So, by the way, he doesn't say that that's a necessary condition. Okay, he says that if that is true, then that condition is satisfied. So it's sufficient, but it may not be necessary. He doesn't discuss that issue at all. By the way, for condition 3, he really struggles with this, he and the two authors, I'm sorry, really struggle with this, try to figure out a method of determining whether the data is elliptically symmetric with very little success. And it's clear they weren't able to do much with that. So when I was first read that paper, by the way, I got that paper not because I like to read complex Annals of Statistics papers, but at the time, one of the things I sort of thought was innovative in teaching the 570 sequence, I would find a whole bunch of papers on regression modeling in multiple journals, and I would Xerox them, copy them, and then I would put them in a big folder, and I told the students that instead of an exam at the end of the course, what they had to do was pick one of those papers, read it carefully, and then present what was in those papers to the class. And my reasoning for doing that was that these are graduate students, and I wanted to give them a feel for research. And I was hoping that at least in some cases, they would follow up with these topics and maybe even do their PhD thesis on them. And that happened on 2 occasions, actually. So unfortunately, I looked at condition 3 and I said, well, so what? So what if you need this condition to be able to make this inference that what you're estimating provides information about the truth, but you can't prove that this is correct, this condition, then so what? You know, why bother? It's not really very important. I did think it was incredibly fascinating. I mean, it seemed almost impossible that this could be true. But then you ask the question, which I had to say there, why am I giving this seminar? Okay, well, about 3 years ago, a statistical reviewer of one of the research papers that I was, a co-author of, came back and said the identity link was not reasonable given the problems with the model. I was presenting the risk difference. Well, I couldn't convince him or her with any reasoned argument about why it was the quantity of interest that I wanted to estimate, or that, so what if it violated some of those conditions of the model. But then I had the brilliant idea that I would refer to the proportionality theorem, to the Lee-Duan theorem, and say, even if I'm totally wrong about these assumptions of linear regression model, still proportionality says that I am actually estimating something that's related to the truth. And it's related in a very simple manner. The coefficients I have, you multiply them by a constant and you will get the coefficients for the true model. Well, that's pretty impressive. And the reviewer thought so too. Asked me for the copy of the paper, and the paper was accepted. Now, I don't know whether, again, I'd convinced the reviewer or the journal decided that they didn't care about this. So I started thinking about the proportionality theorem at that time in more detail, because of course I was bluffing the reviewer because if he really got down to brass tacks, I would have to admit that I had no idea whether the theorem held or not. But as I started to think about it more, I realized that not only were the coefficients of the correct link, of the link I'm using, proportional to the coefficients of the true link, but if I was comparing two different models, none of them which were true, the coefficients of those two models would also be proportional. Well, so that seemed really interesting because that gave me a way to essentially see if the proportionality really holds. Because I could take two models, I could do the linear link and the logit link and the Poisson link and you name it link. And if I could show that those coefficients in those models were proportional to each other, then I essentially had validated the Lee-Duan, the proportionality theorem. Well, I can do that, at least empirically. I might not be able to do it theoretically, but I can do it empirically. So I started to do that. So because I'm involved in the MESA study for many decades, the multi-ethnic studies of atherosclerosis, that's data I know well and I had access to. I decided to see if the theorem held. So in the first example, I'll show I look at the outcome, which is the presence or absence of coronary artery calcium in the coronary vessels of the heart. So in other words, the arteries of the heart will calcify over time. They'll get little calcium plaques on them. And the more of those calcium plaques you have, the worse your risk is. And they quantify the amount of calcium, but some people have none. And some people have some, and even a great deal. But one thing we were interested in one of our papers was what predicts who has any calcium? That is, not having any is good. Having even a little is not so good. Having a lot is terrible. But what predicts whether you have or don't have coronary artery calcium? And in this case, for somebody who knows MESA, this is exam 5 data. Otherwise, they would wonder about where these numbers came from. And so I basically did a model, many models, 5 models, where I use 5 different links to model this risk, this outcome. And I had 15 risk factors. Okay. 5 of them were more than 5, 6, 7, 8. 8 of those, 9 of those variables were discrete, binary. Okay, variables. Clearly, elliptical symmetry was not possible. And so, you know, I thought, okay, this is a good example to try it on. So I did that. And I compared the linear, logit, Poisson, probit, and log-log links. By the way, I don't know what the log links is used for. Probably somebody here does. But in any event, I did those 5 links. I actually did a few others too, but they all gave the same answers basically, so I didn't care. And the first thing I did was to see if the coefficients of the various models were linearly related to each other. Because if the proportionality holds, then the coefficients for one model should be k times the coefficients of the other, where k is a constant. So I did that, and the first thing I noticed very, very quickly is that, boy, could you predict one set of coefficients from the others? Namely, the coefficients were in fact proportional. And I had a lot of slides about the proportionality of what the results were, but I really wanted to make this talk relatively short, so I've skipped most of those. But I'll just show you one. One way to measure linear association is through correlation coefficient. Very simple measure. And the higher the correlation is, the more strongly the variables are linearly related. Well, I was shocked when I did this analysis, by the way. I just couldn't believe the results, really, because here's what I got for the correlation matrix. Well, have you ever seen anything correlated with correlation 0.999? Never. Why were these coefficients so strongly related to each other? In other words, once I knew what these coefficients were, the proportionality constant, I could predict the coefficients from the logit model from the coefficients of the linear model. I would just multiply them by the constant. To me, that was a really, really remarkable result. I did not expect it at all. So I've used this for other reasons in a minute I'll discuss, but then and again, I'm not showing a large amount of output I have about, you know, what these coefficients look like and how they might be used and so on. But the point is that what it implies is that not only can I estimate the coefficients of the model by just multiplying my coefficients from my wrong model with their correct model, I can also estimate the prediction from the model. That is, if I'm using the logit, I could estimate the logit from the coefficients, multiplying them by the observations, by the x's. And that quantity would be correlated almost perfectly with the same quantity computed with the estimates from the other link. So in other words, in a sense, it really says that almost all the information in the data is captured whatever the particular link you're using. It doesn't seem to matter. So the second example, and again, I wanted to leave time, which I am doing very well at, for talking about the prehistory of the department. I did a second example from Mesa where the outcome was CHD incidents and during 10 years of follow-up. We have a nice, Robin was the key author of this paper, the first author, and we have some nice results that show that you can really estimate CHD well, particularly if you add coronary calcium, which I talked about briefly before, to the model. I'm doing the model without coronary calcium, but I'm using the same 13 risk factors. Again, a number of them are binary variables. And again, I did the same analyses, namely I paired the various links, estimated the coefficients from the two different links, determined whether I could estimate linearly with just a constant multiplier, the coefficient from one link to the coefficients from the other links. And I did that. And again, just showing that descriptively what the results were. And by the way, here I actually included the Cox model with time-dependent various outcomes. Well, what's really odd, again, surprising, is that I can estimate the coefficients from the Cox model from the linear regression model quite well, assuming I knew the constant. Okay, and I can estimate the constant if I wanted by computing both both sets of coefficients, but of course that's circular reasoning in a lot of ways. But nonetheless, it's really remarkable that the association between the coefficients is so strong, even when the models are so different. Okay. And again, I have lots of other results I could have shown, but just trying to sort of finish this up quickly. Risk difference is the quantity of interest. I can estimate the risk difference from linear regression, the identity link, and then I've given you two examples that show that the proportionality seems to hold. Now, two examples doesn't make for a theorem. And it's certainly very possible that one can come up with examples where this doesn't hold. By the way, I did try this on other data sets with very different sorts of variables. And in every case, it seemed to hold. Now, one other quick comment that I meant to make earlier is that Cox was here giving a seminar to the department. And in the course of the seminar, and I can't remember what the context was, he said, you know, I've noticed that the coefficients from these two models look to be proportional. And of course, I was ready to leap up and say, oh, I knew that, lead to on theorem. But Cox was really a big name in the field, and I wasn't. And there were a lot of people in the audience who knew Cox well, or at least somewhat. And I never got it. I certainly wasn't going to raise my hand and tell him that. And so, you know, I never got a chance to talk to him about it after the seminar, which was unfortunate. Okay. So what are the insights I've gotten and what are the implications? Well, the insights I've already talked to you about. Namely, it's pretty hard to argue, I think, that if my coefficients from the model I think are important to estimate, and you have another set of coefficients that you think are important to estimate, there's no real way to choose which one's right or wrong. And in fact, the fact that they are proportional to each other, that one can be determined by a constant times the other, really means that you can't really argue from the data that you have that one model is better than another. That they're not better. Both of them are, in a sense, representing the truth up to a constant. I know if that's enough to you, that's fine. If it's not, that's fine too. The implication of the theorem goes further. And if I had more time, I would have presented much more about this. But it turns out, if you'd want to just classify, if you want to do a classification, in other words, you want to take the score that you get from the model, that is the linear combination of the coefficients times the variables from the model, I'll call that a score. It's a prediction of the model itself, not the model, not the probability, but the model. Okay, so I'm gonna predict the logit or the Poisson link or whatever. then if you want to do classification, that is, you want to get a rule that says, if my outcome is greater than this value, I would classify the person as being in group 1. If it's less than that value, I would classify them being in the group 0. Okay. Then the Lee-Duan theorem basically shows that when it's true, the models will predict exactly the same. Exactly. So it doesn't. So if I want to do classification, and somebody says, "Oh, you need to use a logit model," that's wrong. It doesn't matter. I can use any of these models, and I will get exactly the same result. Now, again, I'm talking generalities, and there's a lot of probably special, less than special cases where this doesn't hold. By the way, even for Cox model versus linear, I can estimate the 10-year mortality, say, of something with a linear regression model, and I can get roughly the same result as if I use the Cox model to get that probability of, say, a 10-year risk. And again, it comes back from the proportionality of the coefficients. So the question I'm sort of asking you, because it's the one I've struggled with a long time, and further, it's one that I bounced off a few other people trying to get them to tell me, is this interesting? Is it important? Or is it just some funny thing that I got interested in and has no meaning whatsoever? So I'm giving this seminar in part to get an answer to that question. And whatever it is. I'm an empiricist, so I will listen to what people think. Clearly, the theorem is true for cases that don't meet the criteria that Lee and Duan specify as probably what needs to be met. And so I think there's a fair opening here to do theoretical research, if not simulations or whatever, to try to see, are there less restrictive assumptions that can be made where the theorem will still hold? Now, I believe that's true. That there's no way that the multivariate normal or elliptical symmetry will be met. But clear from the examples that there must be some other condition or reason that this works. And then finally, I gave this seminar in part because for me to continue this research, I need a collaborator who's much stronger in mathematical statistics than I am. Over the years, one thing I've always learned and always believed in is that you should know your limitations. That you don't want to try to do things that you are incapable of doing. Well, I'm incapable of doing mathematical statistics today. Long time ago, yeah, maybe. Now, absolutely not. So I'm looking for a collaborator. And if anyone's interested, please contact me later. Okay, so I will end with that. And I want to drink a drink of water. And then I will talk to you about the prehistory of biostatistics. Well, this prehistory is going to be very much, we can shut that off if you want. I'm not going to do slides. Okay, this is informal. The prehistory of biostatistics, or the history of biostatistics at the University of Washington is a very egocentric thing. That is, I'm involved in all of it. So you will hear this from my perspective. Okay, and if I've I've said that I did more than I actually did, or take credit for more than I actually did, well, you won't know the difference because you weren't here. So, because no one is still, as far as I know, I don't know if there's anyone who was there. Well, yeah, there is one person, yeah. There's at least one person who was there when I came to the University of Washington. But anyway, so no one else is going to be able to tell you this or tell you what I'm saying is incorrect. So let's start. I graduated from UCLA, as was said earlier, in 1964. I came to the University of Washington not for the reasons that Tom said, because there was no Department of Biostatistics. There was no collegiality. There was one person who was the only biostatistician. Well, there actually were two biostatisticians. One was a newly hired, more senior person who was well, I should start over again. I did not go to a Department of Biostatistics here because there wasn't any. I went to the Department of Preventive Medicine in the medical school. Well, you might ask, why would I accept the position in the Department of Preventive Medicine when I was a biostatistician? I graduated from UCLA that had a biostatistics department in the School of Public Health. I was offered positions in other schools of public health. North Carolina offered me, and they told me I'd earn twice as much money there as I would at the University of Washington. But I would have to do a whole bunch of consulting to do that. And that was in a School of Public Health. I interviewed at Pittsburgh. They offered me a position. The chair of the department there was Donovan Thompson, whose name may be familiar to some of you. And as I was interviewing, he said, well, where have you gotten other offers from? And I said, well, I got an offer from North Carolina, I got an offer from University of Washington. And he said, well, you don't want to come here to Pittsburgh. You want to go to the University of Washington. And at the time, I didn't quite understand why he felt that way. But about 5 years later, he joined the Department of Biostatistics at the University of Washington. So he had some inside knowledge that I didn't know about. So anyway, by the way, the reason I came here was to say nothing to do with collegiality, nothing to do with the amount of strong statisticians that were here. It was because it was in a medical school. I didn't want to be in a school of public health. Even though I came from a school of public health, I had no interest in health services. I had some interest in epidemiology, but not a lot. Environmental health, oh, well, so what? Yes, environmental health is important. I wanted to be in medicine because I was really interested in medicine. And if I could have been a physician, if I had the kind of personality and tolerance for blood, I probably would have gone to medical school and become a physician because I was very interested in medicine. From early on, I was interested in medicine. But so I thought, well, being in biostatistics, being a biostatistician in the Department of Preventive Medicine, in the Department of Medicine, was a good thing. And by the way, the other thing I didn't realize when I accepted the offer is I was going to be an instructor, not an assistant professor. They only told me that after I accepted the position. But it wouldn't have mattered. I mean, they told me that, well, the medical school requires that, which they did. And you had to be 2 years an instructor before you could become an assistant professor. Okay. So that's what I did. The pay was half what I would have gotten in North Carolina, but it shows you where my values were. So anyway, I came here. The division chair of biostatistics was Ed Perrin. There was a faculty member who had been there before Ed. His name was Blair Bennett. He seemed to be, I didn't know exactly who he was or why he was in the biostatistics. They had squirreled him away in a deep dungeon room at the bottom of the health sciences building. And it took me a while to find him, literally. And I thought he was fine. I didn't think Ed Perrin liked him very much. I think they wanted to get rid of him, basically, but they couldn't. But I found him very valuable. In fact, the very first time I actually used the risk difference model was when I went to see him, and I asked him, but he's a great guy and really knew statistics. I asked him, I have a binary outcome here. How do I analyze it? Logistic regression didn't exist then. I had no idea what to do. I knew it was wrong to estimate. No, he said, no. He said, what you need to do is do linear regression. I said, why? Well, he said, Fisher has sort of shown that, you know, the linear discriminant analysis justified the use of modeling the binary variable. And I nodded, said, okay. So that's what I did. I had no idea I was estimating the risk differences, by the way. To me, those were just coefficients. I had no idea what they measured. I mean, they measured something about predicting this outcome, but, you know. So anyway, what's the next step in this history? Well, we had a division. We didn't teach any courses because there are no students. Well, we did teach a course to the nursing students. Once a year, the nursing students had to have a statistics course. I don't think we ever taught anything to the medical school until later. So what did I do during those first years? Well, I was telling my wife, the first 6 years when I was in the Division of Preventive Medicine, Department of Preventive Medicine, I have almost no recollection of what I did. My only recollections were, one, when I first got to the UW, I was given an office that I shared with a sociologist, and it was in the medical complex. And for some reason, he didn't like me, or he didn't like sharing an office, I don't know which. And when I learned after a while being in that office, that when I got calls when I wasn't there, the guy told people they never heard of me. And so obviously I didn't get any messages. Later on, I'm just giving you a feel for what it was like to be a biostatistician in this era. Later on, I was given a better office, I guess, better in some ways, that was in, I don't know if many of you know the F wing, but on the second floor of the main corridor was it was an office then. Now it's the coffee shop like thing, you know. There was an office there, and I was given that all. I was sharing with 3 people, one of whom was a microscoper. I can't even pronounce it right. He did microscopy, used the microscopes, and he would take pictures, okay, from the microscope. And it turns out he needed to dry those pictures. So he had a drying machine in the office with these 2 other people, vented to the outside, and often that would be running, blowing hot air into the room with us. And that didn't smell really good either. That I was in that office for several years at least, and I can't remember how long. Anyway, doing those sort of 6 years, sort of went along, doing my research, occasionally teaching a class. I actually taught a class in statistical genetics, the first one taught in the University of Washington. Nothing like statistical genetics is today. And, you know, I had 20 students in there, you know, given that nobody knew anything about what I was doing. And the author was C.C. Lee. I don't know if any of you know the name. But in any event, I taught that course. I actually taught a course for the medical faculty, which I advertised. And I had a class of about 20 physicians. And it was a really good class. It was fun. They really wanted to learn what I was talking about. They had read articles in the literature and wanted to understand them. So it was good, great time. I taught the nurses class a couple times. That was sort of strange. Anyway, going on, about, I say, there's a 6-year gap when I remember very little. I was doing my research, you know, and puttering around of whatever I was doing. I was doing consulting with some medical school people. And about 4 years after I was there, I remember something. a faculty member from the fisheries department came to talk to us, the two biostatisticians in the department, about the idea of forming a graduate program in what he was calling biomathematics. And he needed, to have enough biomathematicians to actually do something. So the mechanism, there was no way he could we could get a department because it was multidisciplinary. Fisheries, medicine, who knows what else. Statistics, no, there was no statistics in the math department, maybe statisticians in the math department. So we approached the graduate school about forming a group. And a group is an academic program out of the graduate school. It gets no funds from anybody. Okay, it gets funds from the departments that feed into this group. But it allowed us to offer a PhD. And the graduate school agreed to us doing that. And so we could give a PhD in biomathematics. Well, we actually interpreted that very broadly. So we were also giving a PhD in biostatistics. Okay. And we started with 3 students. One was a biomathematician, he said. That's what he wanted to do, biomathematics. The other 2 were in biostatistics. The one who said he was a biomathematician was actually a student who fled the mathematics department because they didn't have any statistics at the time, or very limited. And he didn't want to get a PhD in mathematics, which was his option, probably because he felt he couldn't do it. I don't know. However, it turns out he actually did his PhD with us. I don't know whether he had what you'd call his PhD, but it was really biostatistics. And later became a faculty member in the statistics department when it was formed. And he had a joint appointment with us for a long time. He was brilliant, by the way. It was not like he was some slouch. He was quite brilliant. Anyway, so we poked along for a while with this group. I was the chairman of the group. And the first thing I did when we formed the graduate program was that I modeled it after the UCLA graduate program that I graduated from, not surprisingly that I would do that. And some of which were unique at the time, some of the unique things that the biostatistics department at UCLA had was that the students had to take a theory course in statistics from the statistics or math department. That was one of the things that you had to do to graduate. You also had to take a theory exam in statistics. You had to take a theory exam in biostatistics, and you had to have a project involved with medicine or public health. Okay. And in my case, my project was on basically the genetics of fingerprints, inheritance. And I did it with Bob Day, who became Dean of the School of Public Health here. I had a lot of ties between UCLA and UW. Anyway, by the way, Bob Day wanted me to go into medicine, and argued I should go to Miami where I could do a 3-year medical course. And I said, no way. So anyway, those were crucial aspects of the way what our requirements were for the PhD. There's one other requirement from UCLA that I did not want to have here. And that was that you had to take exams in 2 foreign languages in order to graduate. I absolutely hated doing those exams. And I don't know how I ever passed them. I really don't. I was terrible in languages, really bad. But I was all pretty good at memorization. And so I memorized, some of a book from Laplace, I could pick the book I used to memorize from and have to pass an exam on, write up a paragraph from the book. And it was terrible, but I didn't want to have that here. So I decided that what we would have is you could do an exam in a language if you wanted, or you could do an exam in a programming language. Okay. Very few people took the former. So anyway, I was chair of the biomathematics group. Actually, for 13 years, I was chair of the biomathematics group. From 1972 to whatever 13 years later is 1985. And we started out with 3 students. And by the time I stopped being chairman of the group, although this is where I might get fuzzy and maybe Pat Wall remembers better than I do. We became a department of biostatistics at some point, and I don't remember the transition between the biomathematics group and the Department of Biostatistics. But ultimately what happened is all of the students were biostatisticians, biostatistics students. None of them were biomathematics students. So once we became a school of public health, there was a desire on the chairman's part for us to become a department of biostatistics and have a graduate degree in biostatistics, which we had to get permission from the graduate school. So anyway, in that time though, the program grew from 3 students to 20. And most of my effort was in funding support for the students. I would badger all the physicians I knew in the medical school. And one of the advantages of being taught at the medical school, they had money. And often they needed help. So we did build the program. By the way, we're only a PhD program. We did not take master's students. And that was because that's where I thought we should be. Since I was the one in command, so I could do anything I wanted, basically. So we only took PhD students. I didn't want us to be a department like some of the others where they mostly turned out master's students. And I just didn't want that to be our department. I wanted to be a department that did PhD students. And, I shouldn't say this, but I was really unhappy when I saw that the department was moving more and more and more to doing many master's degrees. Not that I have anything against master's degrees. I think that there's a need for those kind of people, but I just didn't want it to be us that supplied them. And the thing is that, of course, we did that in large part because of pressure of money. You needed to have master's students in order to have more money, basically. And that was the rationale. Anyway, I think that sort of summarizes all that history before we became a department of biostatistics. The one thing that did happen is, why did we become a school of public health in the first place? And the answer is money. Department of Preventive Medicine was working perfectly well in the medical school, but there was money available from the federal government to form schools of public health. And money talks. And so we had a big faculty meeting where the faculty involved environmental health people and involved people from epidemiology, some health services, not very many, but it was we had a unit that did microbiology research. Okay, so we had a big meeting, everybody, and we voted on whether to become a school of public health or not. I think I might have been the only person who voted no. That's the way it went. You don't always win your battles. Anyway, then we became a school of public health, the Department of Biostatistics. We started with only 3 people and about 3 faculty members. The one who was in the balls of the medical school left. I don't know why. He probably got waved out or something. I don't know. Anyway, we had 3 faculty members. It grew from there. Our first graduate student was Pat Wall. At least my first graduate student. There were some others, but my first graduate student was Pat Wall, who had an illustrious career. I take complete credit for. Well, I should. I recruited her. I was her PhD advisor. I obviously have some credit. Anyway, yeah, I'm glad to ask questions about anything, including the talk. Maybe secondary here.
Questions? Yeah.
Just a kind of a thank you day in all regards, and that's intriguing extra history that only reinforces what I'm saying. When we compare the difference of what we had in 1965 when you came, when I came in 1984, you came, and then we got Ross, and we got Donovan, and Norm, and then obviously Matt was a student at State, Paula, Al, and others. What you did when you got here, and it's well motivated what you did, but well, basically you were joining preventive medicine and medicine. And what you guys created here over the years was the School of Public Health in 1970, the biomath group that was 72 to 86, and they're just until I came. But then you formed Biostat. You guys formed STAT too. STAT didn't come until about 1982.
Right.
And so what you guys did collectively here was to create, that didn't exist, a remarkable program of biostatistics. And as you said, that culture wasn't here when you came. It was here when I came, and you guys are. So I stand by everything that I said. What you did, the boss, and the other leaders in the department really created a remarkable culture that those of us that took that.
Thanks for all of it.
I was wondering during your 6 years in medical school and having to breathe and come across the air, whether there was some hallucinogenic properties there. Not remembering much.
Well, that's probably the truth. You're probably right. I was wondering why I forgot all that stuff. Now I realize.
Fair Glennon, I never met him. He went on to a career in play, right?
Yeah.
So that must have been quite a switch from a dungeon.
Yeah, well, yeah.
I was curious on that part of your talk. Your funding came from actually from the state during those early years, or what was your personal funding?
It came from Department of Preventive Medicine.
Through state money that they had?
I don't know. No, it came from the medical school. I have no idea where the funds came. Nobody ever asked me about any of that stuff. So I don't ask, don't tell. Yeah.
So other part of your talk was fascinating. So you emphasized communication and so on. Your appearances. So I think one of the reasons for interest in hazard ratios, for example, odds ratios, is the likelihood that you get more parsimonious models setting when you focus on those as part of the people. You're not so susceptible to influence and possibility of absolutely. That's really true.
understood, and I still understand that that these other methodologies or other quantities may be of interest in some circumstances. Okay, I don't doubt that for a minute. And I'm less critical of them now, actually, because of legal wonder of the proportionality.
It'll just say that I agree with you that it's incomplete. Focus on it as you read.
Yeah.
So they're in reports that we publish for other audiences should bring in something about absolute risk effects. But you can do that in a two-step way, and it preserves maybe a little more efficiency of progression steps. Initiative.
Yeah,
Discriminant analysis versus.
yeah. I do understand that, but then I don't understand why the coefficients are so strongly related. That's where the disconnect comes for me, is that if these other estimates have better properties, why can't I estimate them only with using one extra parameter, the constant? How, why are the other method, the ones I'm like doing the risk difference, why is that not as good in some sense? And no, I do understand the theory. I've been Richardson and staff, and I've had some conversations, and I do understand that there's some nice mathematical properties of other estimates, and the question in my mind still is, if we can't interpret them, does it matter? If we can interpret them properly, and if they're interpreted properly by the people who use them, namely the physicians, then I don't have any problem now at all with these others, because of the very reason they just said, proportionality. And in that sense, that's why I think the results of the Dion theorem is really actually kind of important. It's changed my worldview about estimation of parameters.
By the way, on the worldview, you might mention in the early years, even before I was here, there was some considerable convenience.
There was.
Doug Chapman, you can say it.
Yeah.
On site.
Yeah. Yeah. It's true. A lot I don't remember about that period, to tell you the truth. It was kind of amazing trying to think back over things that occurred so long ago. It was just a weird thing. I was always a person who never looked back, literally. I mean, that was just the way I was. I only barely stayed in the present. I was always looking to the future.
Yeah.
Really got me going. Yeah, I was going really fast. So yeah, but it was an interesting experience trying to remember things, because I haven't done that. I just never done. I remember things that I didn't know I knew. Okay. Thanks, everybody. Gee, I really appreciate everybody coming and just all the friendship.
There's
Been
one
great.
question, if you don't mind.
You mentioned the wonderful bias, and I think you mentioned softball.
As Pat well knows, and fun others that, yeah, one of my claims to fame was that we had a co-rec softball team that over a period of about 15 years, we had 128 wins and 9 losses. We had pictures on the wall. If you're looking for when they're posting we had the whole.
The important aspects of the past year.
Yeah. Not the important ones, but the memorable ones. I remember that.
And football too.
Yeah, we were pretty good in football.
And champion.
Basketball as well, we were pretty good, but we didn't have this softball. Really excel. So thank you, everybody. Nice luck.
Thank you.